Computers do not operate on magic. Computation is a rigorous mathematical universe where raw data aligns into predictable patterns through a sequence of specific steps. This sequence is the algorithm, a finite set of well-defined instructions designed to solve a specific computational problem. Algorithms rely on a deterministic structure, ensuring that specific inputs consistently produce the same predicted results through a rigid logical path. Every algorithm follows the same architectural pipeline. You begin with a starting state, the input. That data is fed into the procedural mechanism, the algorithm itself, which processes it to generate a definitive final state, the output. This strict pipeline is what transforms disorganized raw data into a reliable, repeatable tool for computation. To be mathematically valid, an algorithm must satisfy 5 absolute constraints. Without these pillars, the underlying logic is computationally invalid. First, it must accept 0 or more inputs. Second, it must produce at least one output. Data must enter the system, and a calculated result must exit. The third pillar is definiteness. Every instruction must be completely unambiguous. You cannot instruct a computer to simply process a variable. You must provide absolute mathematical directives. Fourth is finiteness. The process must eventually stop. A program caught in an infinite loop lacks a guaranteed termination state, rendering the logic broken. Fifth is effectiveness. Every individual operation within the algorithm must be basic enough that it can physically be executed by the machine, step by step. If an algorithm fails to meet any one of these 5 constraints, the entire logical structure of the program is void. Consider 2 separate programs designed to search a database. Program A finds the correct record in 1 second, while Program B takes 10 seconds. Both yield the exact same output. Measuring performance with a stopwatch is an unreliable metric. CPU power, available memory, and system states fluctuate, meaning the same code will perform differently across different hardware. The real test of an algorithm occurs when the input size expands. We have to consider how these programs behave when the record count shifts from 10 items to 1 million. An algorithm that functions well on a small dataset may stall or fail when faced with massive, expanding inputs. Objective performance measurement requires a hardware-independent mathematical model. By evaluating the logic itself, we can determine how the algorithm scales, regardless of the machine it runs on. We measure an algorithm's speed through time complexity. This involves the rigorous mathematical counting of the foundational computational operations the algorithm performs. We are not counting clock cycles, but rather theoretical steps, such as reading a variable, performing addition, or printing a result. If an algorithm reads an input and prints it, those are 2 fixed, non-repeating instructions. This resolves to the equation T of n equals 2, which is categorized as big O of 1, or constant time. When we introduce a loop that iterates based on the input size, the operations scale in a 1-to-1 proportion. This translates to T of n equals n, or linear time. In a nested loop, the operation count multiplies. An input of 3 triggers 3 outer cycles, each containing 3 inner cycles, yielding 9 total operations. This results in T of n equals n squared, or quadratic time. Abstracting code into these polynomial equations allows us to predict an algorithm's limits before it is ever executed on physical hardware. A Cartesian plane allows us to map exactly how these different algorithmic complexities scale toward infinity. The linear trajectory of big O of n shows stable, predictable growth. As the input data increases, the operation count increases at the same steady rate. Big O of n squared behaves differently. As inputs scale, the required operations curve sharply upward, rapidly outpacing the linear model. This divergence proves why algorithms with linear complexity are more sustainable for large-scale data processing than quadratic systems. Speed is only one factor. We must also evaluate space complexity, which is the total memory footprint an algorithm requires during its lifecycle. Space complexity is the sum of two distinct types of allocation, the fixed part and the variable part. The fixed part consists of the compiled code and static variable declarations. If a program uses 3 fixed integers, the memory footprint remains constant at big O of 1 space. The variable part is dynamic. If an algorithm initializes an array of size n, it demands expanding memory allocations as the data grows, resulting in big O of n space. Optimizing for processing speed while ignoring the memory footprint leads to resource exhaustion, where hardware can no longer support the algorithm's demand for data storage. We can see how these tools apply by analyzing a sum of n algorithm, which finds the total of all numbers from 1 to n. Initialization sets input n, sum to 0, and counter to 1. While the counter is less than or equal to n, it adds the counter to the sum and increments. Once n is exceeded, the loop terminates, the sum prints, and the process stops. Mapping the logic in a flowchart confirms that the process is definite in its steps and finite in its execution. A dry run allows us to track the variable states as they shift. For an input of 3, the counter iterates 3 times, updating the sum at each step. This simulation bridges the flowchart and the mathematical equations. The core loop executes exactly n times, giving a linear time complexity of big O of n. Only 3 variables, n, sum, and counter are used, meaning space complexity is constant at big O of 1. This table organizes asymptotic notations into a standard framework, allowing for the direct comparison of performance across different logic models. Physical code provides the implementation, but mathematical modeling allows us to predict how that implementation will behave under extreme load before it is ever deployed.